Well, good evening, everybody, and welcome to our October Café Scientifique. It's lovely to see such a full room again. So, welcome back if you're just reappearing, emerging from your burrows after COVID, right? It's lovely to get out and breathe the air with everyone. My name is John Willis, and I'll be your host this evening. And just to give you I always give a little preamble before the talks, and our speaker this evening is going to be Tyrone Woods, and he's a research fellow, a Plaskett research fellow at NRC Herzberg, which many of you know is up on Little Saanich Mountain, and you might know its sister institution right next door, the Center of the Universe. I'm sure many of you have been there over the years, right? Now, of course, as soon as JWST, the James Webb Space Telescope, launched on Christmas Day last year, I knew there was going to be wonderful opportunities for talks, but I guess it was only really in the summer, which still feels quite recent, that we got the first science images from the telescope and were able to be wowed. I'm sure as many of you in the audience will remember, as we were wowed over 30 years ago when Hubble was launched, right? So I was really very fortunate, and it's nice to acknowledge this, that I was able to invite someone of Tyrone's caliber and experience to join us here this evening, and even more fortunate that he accepted, right, willingly. There's normally a little bit of arm twisting or guilt involved, but there was none of that here. He was very eager to come and talk to you. So I hope you have a wonderful evening. I know I'm going to have a wonderful evening. So please join me in welcoming Tyrone, who's going to speak to us this evening about exploring the cosmos with JWST. All right, thank you very much.
Thanks very much, John. It's a really lovely introduction, and thanks everyone very much for having me. It's a lovely introduction, but it definitely skims over a little bit of mental turmoil in my head because I absolutely love talking about astronomy with people. The bigger the public forum, the better, because astronomy is just I'm biased, obviously, but I think it's such a beautiful science, right? I mean, you're staring into the night sky and you're looking deep and getting these long exposure images of nebulae and galaxies. It's almost like a science of found art, you know? It's just beautiful. And so then I was reading, John asking me, can you come talk, give a talk maybe in October? And I said, oh, sure. By the way, our forum usually tries to encourage conversation, so no pictures, no slides, preferably. Okay. But I thought about, this is great. This is a challenge. So we'll get through it. Don't worry. So John also said that I should talk a little bit about myself. I really don't like to wax narcissistic, so I'll keep it really to just the facts. I'm originally Canadian. Grew up exactly 50-50, 12 years in Montreal, 12 years in Edmonton. Spent about 8 years abroad doing my PhD in Germany, looking into trying to understand the origins of cosmic explosions. Stars are normally pretty sort of quiet, relatively easygoing things unless you get really close to them, but every now and then some of them explode. And that's really strange. So that was basically my PhD, was trying to understand why some stars explode. I then went and did these postdoctoral appointments, as you do, in Australia and in the UK, sort of expanding my breadth, sort of looking into trying to understand more and more about the early universe. And that's how I got so excited about the JWST. It's really just, it's extraordinarily amazing. It's a lucky time to be an astronomer. And I think by the end of the talk, you'll see why. Finally, I got the opportunity, the amazing stroke of luck opportunity to come back to Canada, and not just anywhere in Canada, but to Victoria. Not just an absolutely lovely city. That's pandering. It really is, though. Absolutely gorgeous city. But also, and people don't really know this, John mentioned the DAO, the Dominion Astrophysical Observatory on Little Saanich Hill. If you've, taken the bus or driven around in central Saanich, you've maybe seen this sort of unassuming little dome on the top of the hill. That has, first of all, 100 years of history. Going back to 1918, when it was briefly the biggest telescope in the world, and an enormous legacy of just astonishing accomplishments, measuring the rotation of the galaxy, our home galaxy, the Milky Way, and probing everything from the interactions of stars violently tearing each other apart, all the way to searching the outer solar system for icy bodies. Today, the DAO is not just the home of the center of the universe, where anybody can go and learn about all the amazing things happening in Canadian astronomy from decades ago to today, but also it is the nerve center of Canadian astronomy, really, right here in Victoria. It's the home of the National Research Council's Herzberg Astronomy and Astrophysics Research Center. That's where I work. And our job is actually to manage basically all of Canada's astronomical investments, our telescopes, all across the world and in space, shared with our sister site, of course, the Dominion Astrophysical Observatory in Penticton. And so mostly, for the most part, we're concerned with ground-based telescopes. But increasingly, there's been this focus on space-based telescopes, not just because of James Webb, but also all the way, going back to our legacy with Hubble. Why would you want to go to space? Before we get to JWST, let's start with the basics. Why do we need to put a telescope in space? It seems really expensive, right? Well, there's a couple of key reasons, but to understand why, I need to talk a little bit about a couple of, physical concepts. But it's okay, we'll get through them. So one of them has to do with the spectrum of light. So if you shine light through a prism, think the cover of Dark Side of the Moon, Pink Floyd, right? You spread the light out at an angle that depends on the wavelength of the light. It depends on the energy of the light, spreading things out from red all through Roy G. Biv to violet. That's the range of human sight. And it's extraordinarily narrow. Only about, if you measure the wavelength, maybe you remember from high school, light is both a wave and a particle, but in its wave-like nature, it has a wavelength, just like any wave, measuring peak to peak, trough to trough. Those colors from all the way through Roy G. Biv, red to violet, are organized by wavelength, and it's only about a factor of 2. That's the range of human sight. And that range is not really any coincidence. That's the range at which we evolved to see, because that's the range at which our atmosphere is the most transparent. There's also a big gap in the radio, which is, of course, very, very useful at very, very long wavelengths. But that's another talk. And so if you want to see anything redder than red, the infrared, if you want to see anything more purple than purple, if you want to find Prince out there amongst the stars, then you really need to go to space, because anything else to the blue, to the purple, astronomers say blue because the human eye isn't particularly sensitive to violet, plus some historical coincidences. If you want to look more violet than violet, you need to get above the atmosphere, because ozone and oxygen completely absorb all of that ultraviolet light. It's protecting our skin, but it's really making life difficult for an ultraviolet astronomer. If you want to look to the infrared, redder than red, you need to go into space at some point. Not too much redder than red, because all these other very, very important things in the atmosphere, water, H2O, CO2, which we probably have a bit too much of, all of those things scatter and absorb infrared light. And so again, you need to go into space. So that's one main reason. There's a whole universe of colors out there beyond the narrow range of the visible. And if we want to see that, we need to go into space. The other reason has to do with the atmosphere as well. It's atmospheric turbulence, which you've experienced if you've been on a plane, especially if you've been flying over the Rocky Mountains. Turbulence means random motions in the air, randomly creating little pockets that act as lenses, almost, or kind of like prisms, bending the path of light, creating that twinkling that you see in the night sky, which is, again, very, very pretty for point sources for these little stars. Very, very annoying if you're an astronomer, trying to precisely measure the positions of stars or take a very, very high resolution image. It puts really a fundamental limit. There are some clever ways you can try to beat it down a ways, and people work on that here at the DAO. But fundamentally, you have a really strong limit on just how high resolution an image you can actually take if you're trying to do it from the ground. So again, you need to go to space. You need to go above our atmosphere. That's really, really great unless you're trying to do astronomy. Any questions so far? I should have said at the beginning, please just raise your hand if anything is unclear at all, or if you have any questions. Don't be afraid to interrupt me. So that's why we kind of needed, the case is made there. That's why we needed to go to space for some of the most interesting things that we can do in astronomy. But we've been to space for a while now, of course, and John mentioned this. The Hubble Space Telescope has been an extraordinary success story. So we've seen incredible things. We've been able to measure the explosions of stars across cosmic distances and figure out that the universe isn't just expanding, which we knew. The expansion is actually accelerating. Everything in the universe is getting, on long distances, on cosmic distances, is getting farther and farther apart, and the speed that it's getting farther and farther apart is speeding up. And we don't know what does that. Something called dark energy is the best we can figure. There are a lot of theories, there are a lot of ideas, but we're still working on that. Other amazing things have been able to be done with Hubble. So we've been able to probe the accretion, the spiraling in of matter onto black holes and the effect that has on its environment as matter and radiation are spat out. We've been able to look a lot closer to home and take extraordinary images as the comet Schumacher-Levy crashed into Jupiter, which was just amazingly fortunate timing that we happened to have Hubble in space at that time. And we've been able to do many, many great things over and over again. I think the boldest experiment that Hubble was able to do, I just love the audacity of it. It's just, who would think that that would be a thing to do? Was something called the Deep Field Observation, Hubble Deep Field Observation. The idea is, let's just pick a patch of sky, of night sky, that looks totally empty. There are no stars from our galaxy in it. There are no nearby galaxies in it. It's just totally empty. And let's just stare as long as we can with the best telescope in the world. And let's see what we see if you could go to extraordinary depth. And what they found, over 100 hours exposure time, all added up, starting to reveal more and more faint galaxies. The tiny, tiny pinprick on the night sky, if you held up a grain of sand, you could probably block it out. Filled with galaxies. Very, very far away, so they're very, very faint. But if you take a long enough exposure, you can see them. And each one, billions and billions of stars, and each one, and within them, there must be billions and billions of planets. Just astounding. So, yeah, absolutely.
If that's the case, if they're so faint that you could hardly see them, how do you know that they're filled with billions and billions of stars?
So that's a great question. So the question was, if they're so faint you can hardly see them, how do you know that they're filled with billions and billions of stars? So the idea is basically, we can compare with galaxies that are in the local universe, and we know how those work, and we can look at these distant ones. Some of them are just points, but we can measure their spectra. So again, if you take the light from that point and you shine it through a prism, it breaks it up into its constituent colors. You measure how much light is coming in at each of those very, very specific colors, those wavelengths. And you can compare this with models of the summed up light of galaxies closer to home, and you can see that, oh, this is a galaxy. Even if it's just a point, it looks just like a galaxy. Maybe not exactly like the nearby ones. That's another big tangent we can get into if you want, but we have to start invoking models and comparing, but that's the basic idea. Does that make sense? Perfect. Great question. So, yeah, please. Yes. Betelgeuse. So Betelgeuse is this bright red nearby star that is, definite. It's in our galaxy. It's very close, relatively close to home, mere light years away, and it's trembling on the edge of it. It's in its final gasps. It is near the end of its life. We don't know. We can't predict with a pinpoint accuracy when, but sometime in the next million years, it's gonna go. And when it goes, it's going to be something amazing. Now, it's not going to be too much trouble for us. I can go into a long tangent if you like. There are some out there possibilities if there is a jet we just happen to be in exactly the wrong spot. It could be beamed toward us and we could be in a lot of trouble. But almost certainly we'll be fine. But it's going to be amazing to see if you happen to be so lucky as that to go off in your lifetime. Any other questions? If not, I'll move on. So Hubble was amazing. I mean, it wasn't. It's easy to talk about all of these things sort of in retrospect, but those of us who maybe are old enough to remember, or those of us who've read up on it a little bit may know that it was quite an ordeal getting Hubble built and getting Hubble to fly and getting it fixed. Because what happened was, taking things back a little bit, the idea was originally conceived in the 70s, in the 1970s, just as the space age was really, after the first great swing of the space age, of course, with the Apollo era. But it took 15 years from then to get it funded, to get it built. And then when they got it built, there was actually a big problem. There was an error in the construction, in the refined smoothing out of its primary mirror. It was off by 1/11,000th of an inch. And the result was it needed a little bit of a correction, right? It was doing okay, but it wasn't really doing any better in terms of its resolution than if it had been a telescope on the ground. It took another 3 years for us to get up there and to install, first to reverse engineer exactly what was wrong with the mirror, and then to get up there and build corrective mirrors such that we could actually fix it. And Canada had a critical role to play in that, and finally making Hubble everything it could be, because that would not have been possible without the shuttle and without the shuttle's Canadarm in order to operate on the Hubble telescope and perform that corrective surgery to fix its sight. So that's already one key Canadian contribution there. But maybe the more continuing, ongoing Canadian contribution to Hubble, again, connects directly to Victoria, because the Canadian Astronomy Data Centre, one of the primary housings for all of Hubble's data, is located, again, right here in Victoria and headquartered up at DAO. And over the years, that mandate, by the way, has expanded and expanded. DAO is now home to decades of archival data from a host of telescopes, providing also lots of software and tools so you can search through it, you can reduce the data. It's just an invaluable resource, and it's just amazing to be working right next to it. So that's all pretty spiffy, I think. How do you possibly top Hubble? What and why? Why do we need to? Well, there's a very, very imminent why, and it's that Hubble, frankly, is getting on in years. There is some talk of being able to boost it. That's an idea that's currently being, to give it a little bit of a kick so that it stays in a survivable orbit. But the fact is, even if you did that, its instruments are getting old. There's a near failure every year or two. Problems are starting to mount. And there's also so much more we can do now that we couldn't do before. And the truth is, even when Hubble was launched, these things take years, decades. I told you about how long it took just to get Hubble built. The moment Hubble was launched, the first thing many people started thinking was, so how do we do the next thing? This is going to live a long time, but it's going to take a very long time before we can build the next telescope. So what do we want that telescope to look like? What do we want it to be able to do such that it can do the same kind of amazing things, but more so, and in a different direction? How can we do things how can we build a telescope that could find things we don't even know we don't know about? It's a tricky problem. So we narrowed things down. I say we, most of this was before my time. But things were narrowed down. To understand how they were narrowed down, I need to introduce a couple of more science concepts. But we'll go through them. We'll do this together. The basic idea, though, is that for a number of reasons, we really, really wanted to build a telescope that's specialty, that's focus, was the infrared, redder than red colors. And that's what ultimately became the JWST. So there's sort of three main reasons for this. One reason has to do with the space between the stars. We think of the space between the stars as empty. Space is a void, but it's not completely empty. There is a thin, thin, thin mist, incredibly low density, lower than anything you could construct even, emptier than the emptiest vacuum on Earth that we've been able to make through most of the space between the stars. But there is matter, and there's gas, and there's also dust. And that dust is also, and gas, get concentrated in some places within our galaxy and within others. And in a few places, they get so concentrated that condensations form within them, more dense clumps than anywhere else. Random happenstance, random motions of gas coupled with gravity, leading to some clumps getting luckier than others, and condense to form stars. And disks form around these stars that form planets. And all of this environment has dust. And dust has an annoying property if you're an astronomer, or useful depending on what you're trying to do, but more often than not annoying. It preferentially scatters and absorbs bluer light over redder light. It's similar to what you see on a hazy day, on a hazy sunset, or if it's if the sky is filled with ash. If you happen to live here or in any area where there's a forest fire spewing out lots of ash and dust, a similar thing happens. Preferentially, bluer light is scattered and absorbed, redder light is let through. So if we want to peer into these, especially anywhere across our Milky Way, within our Milky Way, but especially into these dense clumps, these dense clouds where things are just getting going, the nurseries of stars and planets are being born, it really behooves us to be looking in as redder light, ideally the infrared. So that's one reason. There's a second reason, and it has to do with things that are very, very far away. I mentioned the expansion of the universe, the accelerating expansion of the universe. If we want to look back across the universe, and remember, light travels at a fixed speed, the speed of light, it doesn't travel infinitely fast. And so if we look farther and farther away, it takes more and more time for any light crossing that distance to have gotten to us. We're looking further and further back in time. But if we want to look billions of light years away, towards the oldest things we can see, towards the earliest stars and galaxies that ever formed, we need to worry about the expansion, the accelerating expansion of the cosmos, because this stretches out the wavelengths of light, pulling anything that may have been blue when it was first emitted to the red, to the infrared. And so that's reason 2 that we wanted an infrared telescope, so that we could look for the first stars and galaxies despite this cosmic reddening, this red shift, as we call it. And I think John has spoken extensively about this in at least one of these meetings. The third reason is that atoms and molecules, they have electrons, and the molecules, they have spin states, governed, the positions of these electrons and the spin states are governed by quantum mechanics. They can't just have any old energy, they can't be in any old place. They get locked into specific places, specific spin states of the molecules, and these have specific energies. An electron stuck in that spot, in that atom, would have a specific energy. And it can only move to higher or lower energy states by absorbing or emitting energy as an electromagnetic wave. That's what we call light. So if you shine light through a prism, you can look at Normally you see a continuous, smooth distribution all through Roy G. Biv, from red to violet, or in whatever wavelength range you happen to be looking in, if you have a detector sensitive to that wavelength range. You will see particularly bright spots or particularly dark spots corresponding to the emission or absorption regions associated with particular atoms and molecules. You can identify, oh, this thing has this element in it because I see an absorption or an emission line in it. There are some very interesting lines associated with water and ozone and CO2 that we expect to be able to see in the atmospheres of planets. Indeed, if we had a sensitive enough telescope, in the atmospheres of planets around other stars in the infrared. And so that was reason 3, that we really wanted an infrared sensitive telescope. Any questions so far? Okay. So how is JWST going to be able to do all of these things? Well, first of all, knowing that we wanted to build the most sensitive infrared telescope ever conceived by humanity, we spent years, decades, again, before my time, I say we, it's the royal we, it's not me, pursuing the cutting-edge infrared detector technology that we would need. Thanks to the JWST, we now have extraordinarily sensitive infrared detectors, which have a host of uses, from use on the ground to use in space, observing our planet, understanding how the climate is evolving, understanding agriculture, how things vary over the seasons, looking for minerals and other things. Very, very useful. So developing the foremost infrared detector technology ever developed. Leading edge, bleeding edge. That was step 1. Step 1. Next, we needed to build a bigger mirror. The collecting area of your telescope. What's the area of a circle? It's not always a circle, but what's the area of a circle? It's pi times the radius squared, you may remember. You want a bigger collecting area, you need a bigger diameter for your mirror. And so we wanted to build a much bigger mirror for JWST, 6.5 meters wide in the end. But the problem is that wouldn't fit on a typical rocket, and particularly the Ariane rocket that the European Space Agency was going to be using to launch JWST. So we needed to come up with a just brilliant unfolding telescope, unfolding mirror design. So after launch, the mirror could unfold like the petals of a flower in this kind of neat honeycomb shape, giving us the biggest mirror we've ever been able to put in space for an infrared telescope. Next, we needed to keep the telescope cool. And the reason is, I mentioned infrared detectors. Maybe you've seen footage of an infrared camera. Maybe you've noticed everything is mostly dark but shining a little bit, and us humans, we tend to shine a lot brighter. That's because anything with a temperature is going to be emitting some light. It's not just stars and galaxies. Anything with a temperature radiates energy, and that's light in some wavelength range. And if you want the telescope itself to not be the strongest source of infrared light that it's detecting, you need to keep the telescope really, really, really cool. And so the key thing that was done in order to enable this was to build a massive inflating sun shield, because the biggest problem here is the sun heating up the telescope in space. And so NASA came up with this amazing inflating design. It expands to the size of a tennis court. Finally, to help keep it cool and to also allow it to observe for a very, very long time, do very, very deep single exposures, Hubble was limited because it was whipping around the Earth at about 90 minutes in orbit, roughly. So it couldn't stare at anything for longer, anywhere, even quite that, because it would end up in the shade of the Earth. To make something that could stare for a very long time, we wanted to go all the way out to what's called the L2 point. It's one of these amazing Lagrangian points where the pull from the Earth and the pull from the sun are sort of just right to keep the telescope in place 1,000,000 miles out from the Earth in this case. And so that means, while it was able to keep itself cool and stare for a very long time in this spot, JWST had to do all of these things: unfold its mirror, unfold its sun shield, get all of the tests done and all of the instrumentation in good working order as it heads 1,000,000 kilometers away, where we absolutely cannot go out and service it like we did with the Hubble. Scary. And so that's, as John was saying, we had this 6-month wait from Christmas Day, December 25th, 2021, until June, July. Anyone even a little bit involved in JWST was just on the edge of their seat. What's going to go wrong? What's going to happen? And just amazingly, in a testament to just how much hard work went into all of this and how lucky we all were in putting all of this together, basically nothing went wrong. There was a micrometeorite strike, that's okay, that was planned for. There's some issues with one of the instruments. We turned it off for a little while. I think everything seems to be all right now. But amazingly, basically nothing went wrong. One of the things that we kind of expected to go wrong is we need to use up a lot of fuel getting it into position and getting the telescope into position where it would be ready to sit for the next very, very long time. And you need whatever fuel is left in order to keep the telescope roughly in that position where we want it to be in the solar system. And so the fact is, though, everything went so well that initially we had thought, okay, we should at least bare minimum have enough fuel to make sure the mission lasts 5 years. Let's get a really great 5 years in. 10 years would be awesome. Everything went so well, there's enough fuel left at least. Other things could go wrong, but there's enough fuel left that we think JWST could live maybe even out to 2040, like a long time. It's going to have a good, healthy, long life for a telescope and be extraordinarily productive. So what did we put on this telescope? We have this big reflecting mirror collecting area. We have the sun shield. What are the instruments? What are the observations we're going to make? Well, we have a couple of cameras. We have NIRCam, which is this near infrared camera. So it looks from, the wavelength range is sort of from orange, about 0.6 microns, if you know your wavelengths, to about almost 10 times that in wavelength. So into the near infrared. And then we also have a spectrometer, NIRSpec, that lets us shine that light through a prism, take spectra of objects. Then we have the European contribution, MIRI, which is a mid-infrared telescope that extends all of that from 5 microns or so, all the way out deep into the mid-infrared, into about almost 30 microns. And then we have the fine guidance sensor, and we have NIRIS, the near-infrared imager and slitless spectrograph. Sorry. And the FGS and the NIRIS, as they're called, those are Canada's contributions. And they were developed by the Canadian Space Agency, the National Research Council of Canada, the Université de Montréal, Honeywell, one of our, Honeywell International, a big space enterprise in Canada, and smaller partners and universities across the country. These are Canada's crowning achievement contributions to the JWST, and they're just absolutely astounding. The FGS, the fine guidance sensor, that's what allows, it's an extraordinarily high precision camera. It allows us to do extraordinarily high precision pointing. In a sense, every picture that you're seeing the James Webb take, there's a little bit of a Canadian influence in there because that's a Canadian instrument that's allowing the telescope to point so accurately. And then we have NIRIS. I talked a bit about shining, picking a point, or more often actually we kind of choose a slit on the sky, shining that, letting that light shine through, blocking out the rest, shine through a prism, spreading it, smearing it out so we can look at how much energy is coming in at each wavelength. NIRISS lets us do that across a whole field of view, so we can take an incredible number of spectra all at once. And so we're going to use these instruments, all of the instruments actually, are going to be used by Canadian partners, people right across this country, to do incredible things. Yeah, question?
So it's running.
Yeah.
What have you learned so far?
What have we learned so far? So I'm just getting to that. So incredible things we've already seen. So we saw those 5 images. You probably saw maybe the big press release a few months ago. So we saw an incredibly deep image, something like what the Hubble Deep Field had done. But it was able to do that in hours instead of days. We're already keeping up with what Hubble was able to do, and it's able to see more into the infrared and more sensitively into the infrared than Hubble ever was. So we're finding even earlier galaxies, galaxies that we think are some of the first galaxies that ever formed. The first stars, something we like to call cosmic dawn, because, you know, the first stars rising. We also, using that NIRISS instrument, we were able to study the atmosphere of a planet around another star. This is a favorite of mine that I like to show around. It's not a pretty picture, it's just data, but what it's showing you is the presence from those, remember those features in the spectra I was talking about, of water in the atmosphere of another planet. It's a hot planet, it's a gaseous planet, it's kind of like a Jupiter, it's about half the size of Jupiter, but hugging right close to its star, almost closer actually than Mercury is to our star. It's not a place you'd want to live. You'd probably bake pizza in its atmosphere. but it's a proof of concept that we can detect water in the atmospheres of these other planets. And to be honest, the reason it was released first, it's an easier target. We're going to be doing these harder cases. It's just getting going. And so this is just some of the things that we've been able to do. A lot more is coming because James Webb, the JWST is going to be able to live long enough to do all of these amazing things. Yeah, question?
Can it be retrieved?
Not presently. And so that's why it was so scary if something went wrong, right? So everything really had to be just right. And that, to be honest, was part of why there was quite so many delays, especially the last sort of couple of years. Maybe by 2040, but I'm not going to speculate, if there are significant advances, but it's not something that, right now the plan is no, we'd never be able to get to it. Yeah. Yeah, so they've rebooted it, and they haven't said too much about the present status, but my understanding is that they're confident that everything can be back online in short order. So to be honest, they've been largely pretty mum about it as they've been working on it. They're very conservative, very cautious. They don't like to say anything until they know, but I haven't heard of any particular reason to worry. It's an abundance of caution that they're keeping it, that they took it offline briefly. Yeah, so it does both. It does both camera, so like taking a picture, and also taking spectra. It has 2 different modes, and it does it for the mid-infrared. So that's from sort of 10 times redder than orange, if that makes sense, to in terms of wavelength, all the way out to about 30 microns. So that's way into the mid-infrared.
Are they already planning on the next one?
On the next instrument after JWST. I'm going to get to that at the end of the talk. Is there another question?
Yep.
Couple more. I'll get him first. Yeah.
Yeah, is it orbiting something or is it just going out into space?
So it's sitting out at L2, which is this neat point. As you move out in the solar system, your orbital velocity would be going down. You'd be expecting it to take longer to swing around, right? But there's this sweet spot called the L2. It's one of the Lagrangian points. This fellow Lagrange, a century or more ago, mapped out these sort of sweet spots in the solar system where the pull from the sun and the pull from the Earth could keep it tugged along and sort of stuck in one spot relative to the Earth. And so that's basically, it's not sitting exactly in that spot, it's sort of wavering around it, but that's where it's sitting in our solar system. So out from the Earth in the direction sort of along the line of sight from the sun to the Earth out.
So parking out there, so it travels from Earth at a huge velocity.
Mm-hmm.
How does it slow down? How do they compensate
Yeah. So it has these little boosters. It had us, and that's why we were so worried. It has this finite fuel supply, right? You can't go out and fill up the gas tank. so it has these boosters to slow it down and get it into position. If there had been even a slight variance in the trajectory, it would have cost an enormous amount of fuel to get it back aligned and get it into position. And so we, basically had planned for something to go wrong. The fact that everything went so well means we have an enormous amount of fuel left. And so that's why we think it's going to have such a longer lifetime, to kind of keep it, because it doesn't stay perfectly in spot without fine adjustments. We need fuel left over for fine adjustments.
But the speed it was going at
Yeah.
when it was parked, I mean, they must have been tremendous.
Yeah, I don't remember exactly what the speed would have been, but tremendous, but not so much that you couldn't rocket booster yourself back into. The thing is, nothing is stationary, truly stationary, right? It is moving now. It's still moving. It's still moving with a significant velocity, but it's adjusted itself into this parking orbit. You have to get used to it's something crazy to wrap your head around, that everything is always moving.
It's a solar synchronous orbit?
Yeah, so it's in the L2. So basically, it's always at the same spot along sort of an Earth-Sun line of sight out.
Solar synchronous and Earth synchronous.
Yeah. Make sense? Okay, other questions? Yeah.
So in terms of space junk, are you really going to leave it out there forever?
So yeah, no, in principle, things that are in orbit need to have a plan. Actually, there's a formal plan now for deorbiting objects. So for the low Earth orbit in particular, which has gotten to be a very crowded place, and some billionaires' plans are for it to become an extremely crowded place, you now need to have a plan where when the telescope is or not necessarily telescope, but satellite is no longer active, you need to have a plan for deorbiting it within, I believe it's 5 years. So the idea is to make sure we don't completely clutter the low Earth orbit. L2 is not too busy a place. There's a few telescopes out there. It's going to be in some late 21st century future when we can easily head out there. I bet it would be really amazing to send a rocket out there and start maybe trying to reboot some of these telescopes or collect them. But that's a far future idea. But there's only a few things out there, and there's probably only ever going to be a few things out there. And there's a lot of space in space. So we're not presently very worried about the space junk situation there. That could change. That could change. There was a time when we didn't think low Earth orbit would ever be in danger of being quote unquote full. But it's something we need to keep an eye on, and that's a good point. Yeah.
How often is the telescope working, and how do you schedule time as a researcher to use it?
So the way that it in general, it has a lot of uptime. The issue is it's very slow to point, and so there are a lot of costs and time in terms of the pointing and stuff like that, right? But the way you access it, there are, for nations that contributed directly in terms of building instruments and stuff like that, there is a certain amount of guaranteed time, and with it we have certain guaranteed time programs. So Canada has about a 5% share based on our financial contribution. So we get these guaranteed time programs. For instance, the Canucks project, the Canadian Nearest Unbiased Cluster Survey, unsurprisingly, led by a West Coaster here, is going to be looking at, do you remember that first, I don't know if you saw it, the first image, the one that they did the Biden announcement for, where they had this really deep field? So it was looking at a lensing cluster. So it's not just any old random patch of space like the Hubble Deep Field was. It's a special spot where there is a big cluster of galaxies. This, in that particular case, about 4.5 billion light years away, thereabouts. The cool thing is, Einstein tells us, and it's held up, matter bends space-time around it, and that means it bends the path of light, right? So, how to put this? So, as light travels from more distant objects behind it, it gets bent by the gravity of the cluster. Think of it as a big depression in the universe. There are preferred spots where the light actually gets focused, and you get a naturally occurring lens, which gives you a big boost. It's misshapen, and you have to correct for it because it's naturally occurring. So there's a lot of corrections to be made, but in principle, you have a naturally occurring magnifying glass letting you look into the early universe, letting you look into really, really faint objects behind it. And so the Canucks program is going to be looking at 5 such clusters, lensing clusters, and looking at galaxies over cosmic timescales. How did galaxies evolve? How did they first form? And how did those initial smallish clumps come together to form bigger clumps, to form galaxies like we see today? And how did the black holes accrete and grow and merge to form the supermassive black holes we see at the heart of every galaxy, including our own? And so that's one example of a guaranteed time program. But if you would have an idea, if you would like to propose, you can do that. You can submit a proposal. A significant chunk of time is dedicated to guest observer programs. Every year, you can apply. Things have been delayed because of delays in the launch schedule, but in principle, they're on a regular cadence. You can apply to get time to observe, and it's competitive. It's blind, so we don't know if you're a professor at a university or a student. And everything is evaluated based on their merit. If you have a meritorious application, you can get JWST time. Yeah. John, 5 minutes. Okay, I thought that was a question, John. So I think I got most of that together. So that basically covers a lot of what we're going to be able to do with JWST. So we're going to be able to study the atmospheres of exoplanets. There's another Canadian program I didn't get a chance to mention, Wes Fraser is looking into. We're going to be able to, he's another fellow at DAO. We're going to be studying the outer solar system, looking at Kuiper belt objects. We're going to be looking for the evolution of galaxies across cosmic time and cosmic dawn. All very, very cool things. But there was a question I promised I'd get to. What are we going to do next? So there's a lot of ideas about what we're going to do, once we've done all of this JWST stuff. And actually, there's a lot that's going to be happening over the next decade, even while JWST is flying. JWST has this one annoying feature. It was a design choice. There are a number of trade-offs you have to make, and unfortunately, JWST is looking at a very, very tiny patch of the sky at any given time. So there are a lot of telescopes coming online. The Nancy Grace Roman telescope being led by the United States, the Euclid telescope being led by Europe, by the European Space Agency, that are going to be looking across a large area of sky, although not as deep at any given time. These are wide field surveys, but they're all focused on the infrared. There is actually an alarming gap arising because, again, Hubble is not going to live forever. Hubble can observe a little bit, not well in the infrared, in the optical, and in the ultraviolet. We have lots of infrared telescopes coming online. We have optical telescopes. We don't have a plan for a UV telescope, at least not until the probably mid to late 2040s. And that's actually where not just NRC, but Canada as a whole is taking the lead. We have a plan proposed, but it's in a phase 0 study right now. So this is, judging its feasibility, judging how it's going to work, iterating between the science team and industry to determine what we would like, what's feasible, etc. It'll be up for funding in the early 2024, we hope, probably not too long after. It's called CASTOR, the Cosmological Advanced Survey Telescope for Optical and UV Research. And the idea is to build the premier ultraviolet telescope. I didn't get to talk a lot about ultraviolet here, but in our local universe, any new stars that are forming shine in the ultraviolet. And there's incredible science we can do, again, understanding the atmospheres of planets, studying the outer solar system, studying the accretion of matter, the spiraling in of matter onto supermassive black holes. We need the ultraviolet for these things. And this is something that Canada is actually poised to take the lead on, the foremost ultraviolet telescope in the world in the late 2020s. So that's actually what I'm working on now, and a lot of people across the country and around the world are working on as one of many follow-ups to JWST, as space astronomy just sort of explodes in its importance for the astronomical community. I'll stop there, John.
What a wonderful presentation. I love it when I get to forget my job and just listen with the rest of you guys. Now, there's no more questions, are there? You guys asked all your questions, right? Or have we got a couple
I'm
left
sure there's
over?
more.
Which we're happy to take now. So I'm just going to take a glance around the room because I'm blinded always. I see there's a gentleman there with his hand up.
Yes.
Oh, that's an interesting question. Let me repeat the question, especially for the folks on the live stream. Actually, could you repeat the question? All right. If every time you look somewhere that appears to be dark in the sky, and you see there's what is apparently a plethora of galaxies, maybe faint stars, this kind of thing, why was it dark in the first place? Why couldn't you just see it?
Yeah, absolutely. So, I mean, that's a great question. That actually, I can get to this in a minute if you want me to ramble on, but it actually gets back to a really deep question from hundreds of years ago that kind of gave birth to cosmology, this Olber's paradox. Why is the night sky dark, right? Which was this idea, if the universe is infinite, why, and the speed of light was infinite, why are there, which is what they thought 300 years ago, why are there dark patches of the sky? And of course the answer is the universe is not infinite, nor is the speed of light infinite, right? But to get more specifically to your question, why are these empty patches of sky unless we peer deep enough? They're just too faint. These are galaxies that are, billions of light years away. There's maybe a few stray photons coming in. It's not something that your eye is able to pick up, especially against the glow of the atmosphere itself when you're walking around. And even if you were in space, it's just too faint. You need and also your eyes are not sensitive to this predominantly red light for the really cosmologically distant things. You need a really, really sensitive telescope and a long exposure. Even think of it this way: even if you have a relatively fancy camera, I don't, but if you had an SLR or something like that, digital SLR, and just turn the exposure time way up, you could see all kinds of details in something that you wouldn't normally be able to see just with your eye, because you can use it as a light bucket and just add up all of these photons, right? And so that's why these deceptively dark patches can yield galaxies if you just stare long enough.
All right, just let me cast. Right, I'll do you after this particular gentleman here in the hat. Yeah. I see you had a question.
Has Sheldon booked any time yet?
Sorry, has Sheldon?
Yes.
The guy from the Big Bang
the
show.
guy from the Big Bang, yeah. Not that I'm aware of.
Now, was it that person there? You're lost in the glare, but speak up, please.
Oh, that's you're not the first to say that. Can you just explain the Big Bang, because it wasn't at a single point when it doesn't go out like a circle everywhere, right? It's something different, or is that exactly what it is? And it's expanding faster and faster.
That's it. The easy questions.
But before I repeat this, can I just say good luck?
Yeah.
All
Yes,
right. So the question was, could you explain the Big Bang? And there was some point about it not being the same in all directions. Possibly. Okay. There you go, Tyrone.
I'll try. I'll give it. It has felled many great tests. So essentially, it's easier to think of it. It's really, really hard because it's not an intuitive thing to explain, because you'd need to live outside of 3 dimensions to really understand what's going on here. But basically, it's easier to think of it as, in the beginning, the universe was in a hot, dense state. And then what happens is you basically turn up the scale length, and so that everything just seems to be getting farther and farther apart, right? But sometimes I think of it, this is not a great analogy. I know the usual analogy, although it doesn't 100% work, is to think of an inflating balloon. I almost think of a map, but think of the legend slowly changing what it actually is. That's sort of another way to try to conceptualize, so it's getting to be bigger and bigger. But things that are close together get bound by gravity. They don't ride along on this cosmic expansion. And so in the beginning, we think that there were some quantum fluctuations, which always sounds like an astronomer is trying to mumble over something. But really, we do think when it's it's such a hot, dense state that you really do need to think about, quantum properties on a macroscopic scale, because the universe is only as big as something where you need to worry about quantum properties. And so we think that these quantum fluctuations basically led to some places being a little bit denser than others, and these stayed clumped together while others didn't as the universe expanded. And these give rise, this is your initial seeding kind of structure that leads to these galaxies, and then the galaxies form stars. And that's sort of, I think, what you mean by the why wasn't it even all the way across? That's my interpretation anyway.
Well done. That took me 45 minutes last time I gave a presentation on it, so you've done a much more condensed version. Now, I've got 2 more questions at least, and one at the front. I'm going to whisk through those 3, and then we might thank our speakers. So let me just ask that person there. I can see you.
Sir, what do you think of exploration space as far as the moon base is concerned in Mars?
Yeah, so...
Let me just repeat the question, sorry. So yeah, the question was, what do you think about, one might say, more general space exploration in terms of moon bases and Mars exploration?
No, so I think it's absolutely amazing the time we live in that we're even able to contemplate these kinds of things. I think that, more and more we're genuinely thinking about, so what if we can build the next great telescope, maybe not Castor, but, a decade or 2 after that, could we build the next great telescope on the moon? You don't have an atmosphere on the moon. These are things that we're, I wouldn't say we're committed to by any means yet, but these are things that we're legitimately thinking of. And I think that's just an absolutely wonderful thing to even try to begin to grasp. I think that, with anything, we need to be cautious about how quickly things are developed, and we do need to think about creating the proper legislation to make sure this is done responsibly and things like that. And that opens a huge can of worms that we are running out of time on, but I'll leave it at that maybe. I'm very excited.
What do you think of Phobos?
Of what? Phobos, yeah, no, so the Phobos, he asked, to repeat the question, what do you think of Phobos? So Phobos is one of the moons of Mars. I think it would be a relatively easier target to explore than landing on Mars itself, because you don't have to go down into that gravity well. So yeah, definitely it would be very cool to explore Phobos.
All right, I'm just going to let this lady here ask the question, and then we have a person at the front who wants to ask a question, just to let people know what to expect. So,
Related to the Big Bang.
Yeah.
Listening to some of what the James Webb Telescope is going to be able to do, they're saying it's able to look back in time to fairly close to the Big Bang. I'm not quite sure if that means like 1,000,000 years after the Big Bang or 1,000,000,000 years or what they're talking about. But can you explain what that means?
Yeah, so, keep doing it, yeah.
So the question was, you often hear the phrase that a telescope is a time machine. You're able to look at things as they were in the past. So how does that actually work?
Yeah, so as I said earlier on, so light doesn't travel infinitely fast. It travels at a certain speed, and so the further away we're looking, the more time light must have spent traveling towards us. So in a sense, we're looking at a picture from possibly billions of years ago. And so by shifting to the infrared and by building just an incredibly sensitive detector, JWST is able to, and also piggybacking off of these sort of coincidence cosmic lenses that I was talking about, these gravitational lenses, in some instances, we think that JWST is seeing galaxies that may be in the first, let's say, couple 100 million years of the universe. is sort of what we're talking about. Certainly we're able to probe now within the first billion years, and we think within even a couple 100 million years, some of the first galaxies. It takes time for things to settle down, but yeah.
So just the last question here.
I actually had a couple questions, but that raised another one. But
Y-
anyway,
you get one.
we talked about the black hole.
Mm-hmm.
Why is it called the black hole?
This is a wonderful question. Why is a black hole called a black hole?
So it's actually, etymologically, it's in allusion to a prison that no one was able to escape from, an old prison that was called the black hole, and that's actually where the term came from. But in terms of physically, why is it called the black hole? It's because the gravity of a black hole is so strong, space-time is so warped around it, that not even light is fast enough to escape it. Past a certain horizon, the event horizon, you're not going anywhere. You're just added to the black hole. So it's within the event horizon, and beyond there be dragons. There are a lot of ideas about what happens inside a black hole, but I'm not that kind of physicist. The truth is we don't really know. It's really amazing. I do actually study black holes from the outside. I study the things that go into black holes and how we might make massive black holes. And I think it's just absolutely amazing because I get to work at sort of the interface between astronomy and then quantum mechanics and the real nitty-gritty of how does physics come together. I think a quote that I really, really like, and it's a good one to end on, is that the black hole is the atom of the 21st century, which is ominous, but it's also really, really exciting. The idea is whatever happens in a black hole, you're uniting the physics of the very, very massive general relativity, gravity, with the physics of the very, very small quantum mechanics. We don't know how those match together in much the same way that we didn't understand how the physics of the atom worked at the beginning of the 20th century. We had this idea of this and that, and quantum mechanics was just beginning. Understanding the atom unlocked an enormous amount of new scientific understanding and dangers. I think that the black hole, where these two ends of physics that don't yet meet have to meet, I think understanding black holes is going to be the next big leap forward in understanding physics.
Before we thank Tyrone for a wonderful evening, let me make a couple of announcements to you. First of all, we will be back in November. We have another Café Scientifique. We will be talking about another space mission. But this one is a bit more modest, but no less exciting, because it's coming solely from UVic. So that's going to be an interesting one. You might have heard of it, AUKUSAT. We're going to hear a little bit about the AUKUSAT project out of UVic. Secondly, if you have a question and we didn't get to, please feel free to join us at the stage here after we thank Tyrone. If you want to talk a little bit longer, we'll be here for a few more minutes. So with no further ado, let's say thank you to Tyrone again for a wonderful evening. Thank you, Tyrone.
Thank you very much. Thank you. Wonderful questions. Thank you, everyone.
The announcement at the beginning. But nice to meet you.